We're going to look at rules of exponents, and we're going to look at scientific notation. So let's go over some basic rules of exponents. First rule is if you have a base to the first power, that is equal to whatever the base is. If you have a base to the 0 power, that's going to be equal to 1, as long as that base is not 0 itself. 0 to the 0 is 0. So this first one, if you don't see an exponent, that means the exponent is a 1. It doesn't mean it's a 0. If it's a 0, then the entire expression would have a value of 1. Let's see some other things. If you have a base to a power, and you multiply that by the same base to a power, what you're going to do is you're going to add those exponents together. If you have a base to a negative exponent, then it's going to be the reciprocal of that. And again, this base cannot be 0 because that would mean you'd be dividing by 0. Kind of a combination of those two. If you have a base to a power and you divide it by the same base to a power, what you do is you subtract those exponents, or in other words, you add a negative exponent. Let's see what else. If you have a base to a power and you raise that to a power, then what you do is you multiply those exponents together. And then kind of an extension of this is if you have more than one base going on in here that are multiplying each other, raise that whole group to a power, then what you do is you apply this, what we call this power rule, to both of them individually. You multiply each of their exponents, and if you had 3, you do it multiply 3. But it is important that these are multiplying each other inside the parenthesis, or alternatively, they could be dividing each other inside the parenthesis, and you raise that to a power, then you could apply this rule here, this exponent rule, to each piece. If they are adding or subtracting inside, then it's a lot more complicated doing powers to powers. Don't confuse this for if they were adding or subtracting. That's a polynomial multiplication issue. All right. Let's look at some example problems. Let's say we wanted to simplify negative 3x to the 4th y to the negative 2 times 2x to the negative 5 y to the negative 6. Okay, so what we would do is we would say, okay, we're going to take negative 3 times 2. Those are the two coefficient parts of these expressions, times x, and we're going to multiply our x's together, and the way you do that is you add the exponents. So I'm going to take 4 and I'm going to add that to negative 5. And then I'm going to take my y's and I'm going to add their exponents. So negative 2 plus negative 6. So cleaning this up, I have negative 3 times 2, so negative 6. X, 4 plus negative 5 is negative 1. And then y to the negative 2 plus negative 6, negative 8. Then if it has a negative exponent, but not a negative value, see the 6 is negative in front, but that's a negative value, it's not a negative exponent. The x and the y both have negative exponents. If you have a negative exponent, then that part gets reciprocated. So you can think of everything right here is over 1. So the x flips down to the bottom and the y to the 8th flips down. And notice these powers now are positive exponents. So there's a positive 1 here and a positive 8. When we do that reciprocal, those changes the power. If we go back and we look at this negative exponent rule, we notice when I put it on the bottom here, the sign of that exponent changed. If it didn't, you would be flipping it back to the top, and then it would flip back to the bottom, and so on. So it's got to change there. Let's look at another one of these. Let's say I wanted to simplify x to the 4th, y to the negative 3, over x to the negative 4, y to the 8th. I want to raise all of that to the negative 2 power. So what I could do is I could start by trying to clean things up inside, or what I can use is use that rule that says I'm going to raise everything to the negative 2 power, so I'm going to apply that each way. So That's the rule I'm going to use. And I'm going to go back to this rule that says if you have a power to a power, you multiply those powers. So I'm going to use that rule for each part of this. So I'm going to say I'm going to have x to the 4 times negative 2 power, y to the negative 3 times negative 2 power, over x to the negative 4 times negative 2 power, y to the 8 times negative 2 power, which gives me x to the negative 8, y to the positive 6, x to the positive 8, y to the negative 16. I got a couple options here, so let me kind of show you these different options, and you can decide which option clicks best with you. Option 1 is I'd say, well, okay, I'm dividing. So I can use my rule that says I'm going to take the powers of my x's and I'm going to subtract them. And I'm going to take the powers of my y, so negative 8 minus 8. I'm going to take my y's 6 minus negative 16. And then I'm going to work this out. I'm going to say this is negative 16. Negative 8 and negative 8 make negative 16. This is really a plus 16, so 22. And then I can say, well, if it has a negative exponent, I'm going to reciprocate it. Again, this is like everything over 1. I can reciprocate it, so this x is going to the bottom, but this y to the 22nd is a positive exponent, so it's going to stay on top. So that's one way I can do it. And if that makes sense to you, great. You can do it that way. Let me show you another option. Option 2, what I do is I say anywhere I have a negative exponent, that part gets reciprocated. So the ones with negative exponents is this x term and this y term. So those two are going to switch. But the other x and y are not. So the purple ones are going to stay where they're at while the yellow ones are going to flip. And so what's going to happen? You're going to get, I have a y to the 6 is going to stay on top, but that x to the negative 8th is now going to go down to the bottom and become positive 8. I already had an x to the 8th on the bottom, so that's going to stay there. And then this y to the negative 16 is going to reciprocate. It's going to flip, and it's going to go on top. And now that these are on the same level, I use the multiplication rule that says you add the powers. So y to the 22nd over x to the 16th. You got the same answer. So which option is a better option? It pretty much depends on, how you think about it. If you'd rather reciprocate things and then, see how the lay of the land, or if you'd rather just use the subtraction rule, that would also work. All right, let's talk about scientific notation then. So scientific notation is useful when you're dealing with really big numbers or really small numbers. And what it looks like is you have a single digit, and that's not 0. So it's got to be a 1 through 9, not a 0. And then you usually have a decimal and then some more significant digits. And you take some courses, some science courses, somebody might talk about how to determine what is significant or not. We're just going to, in this course, just say, if it's not a 0, it usually is significant. And then times 10 to some integer power. So it could be positive or negative whole number power. So let's see how this works. The idea here is, let's say I have 2.5. And I say I'm going to multiply that by 10 to the 0. Well, 10 to the 0 is really just 1. So this is 2.5. Now let's say I take 2.5 times 10 to the 1st. Well, 10 to the 1st is 10. So if you multiply 2.5 times 10, you're going to get 25. And if I were to put a decimal there, the decimal would be right there after the 5. Let's say I have 2.5 times 10 to the 2nd. Well, 10 to the 2nd is 100. So if you take 2.5 times 100, you're going to get 250. And again, my decimal would be right there. If I have 2.5 times 10 to the 3rd, I get 2.5 times, well, 10 to the third is 1,000. So 2.5 times 1,000 is 2,500. My decimal will be right there. And so on. You see how this keeps getting bigger and bigger and bigger. What we're going to do is kind of skip this middle step and look at converting between these numbers. And what I notice here is, notice where the decimal is in my normal digit number versus my scientific notation. So this first part is scientific notation, and this is standard notation. So what I'm going to look at is what's the connection between here. And I notice, like, see where my decimal is here, it's exactly in the same spot my decimal's here. So it moved 0 places. Now my decimal, if I notice my decimal here, it's after the 5, but now it's between the 5. So this, you can think of it in this 25, the decimal moved 1 spot in the front, moved 1 spot up, that made this a power of 1. And it moved 2 spots, power 2, 3 spots, so on. So usually what we would do is we would ask ourselves, how many spots do I have to move it so that I get it right behind that first number? So let's say I had this number. So what do we have here? 1,000 millions is 25 trillion. 25 trillion. And I want to write that in scientific notation. So what I'm going to do is I'm going to say this is going to be 2.5 times 10. And then I'm gonna, this is where the decimal is initially. I'm gonna count how far it has to move so that it ends up right behind the 2, right here. How many spaces is it gonna have to move in order to do that? And so I'd say, well, it goes 3, 6, 9, 12, 13 spaces. So this is 2.5 times 10 to the 13th. So that's a way I can write that 25 trillion in this format, this scientific notation format. Same idea if you have, let's say you had 2.5 times 10 to the negative 1. Well, we said that a negative exponent told you to do the reciprocal. So, you can say this is dividing by 10. Multiplying by 1/10 is the same as dividing by 10. And so if you take 2.5 and you divide it by 10, you would get 0.25. And if you take this to the negative second, that would be 2.5 times 10, or 1 over 100, or in other words, dividing by 100. And so that would give you 0.025. And if you took 2.5 times 10 to the negative 3, you'd be multiplying it by 1 over 1,000, or in other words, dividing by 1,000, so 0.0025. And so, just like when we looked at the positive, or the big, positive integers that are exponents for 10, when we're looking at these negative exponents, we're going to look at, okay, here's the decimal right now. I want it to be between the 2 and the 5, so how far does it have to move in order to get right there? And the answer is 1, 2, 3 spots to the right. So notice that's the same as the power. This has to move 2 spots to the right. So if I had 0.000000025, and I wanted to know how would I write that in scientific notation, I would say, well, how far does this decimal have to move? 1, 2, 3, 4, 5, 6, 7, 8 to the right. So this would be a negative 8. The easy way to kind of remember if it's positive or negative is, remember, negative means you're in effect dividing by that number. You're multiplying by 1 over that number. So it's going to be a very small number if you're multiplying by a lot of tens. It's going to be a very, and I mean small value, not length. Obviously, the length of this is pretty long, but the value of it is very tiny. So, you're going to look at, with a negative exponent, making it a very small number. Why do we want to do this? Well, as I said, you can represent, really big numbers or really small numbers using the scientific notation, that makes it easier to do some calculations. Like let's say I wanted to simplify this multiplication of, 2,700,000 times 3,010,000. And multiply those together. So, I could do that as they're written, and if I use a calculator, it probably wouldn't be that hard. But it would be a really long number and keeping track of all those zeros. So what would be easier is if I turn these to scientific notation. So I want to turn this into 2.7, and then I would say, okay, where's my decimal initially? So 3, 6, so 2.7 times 10 to the 6, and this is going to be 3.01. So these other zeros, they're not significant. They're just telling me where I'm at. But this 0 in the middle is significant. So 3 and the 1 are both significant numbers, and the 0 separating them. It's not 31. It's 3.01. So I need that one. And then how many? 3, 6 as well. And so when I multiply these, how I'm going to multiply them is you're going to look at this as 2.7 y to the 6 times 3.01 times y to the 6. And the way you would multiply that is you would multiply the coefficient parts together, and then you would combine the variable parts by adding their exponents. So that's what we're going to do here is we're going to take 2.7 times 3.01, whatever that is, and then we're going to multiply that by 10 to the 6 plus 6 power. So I'm not going to go through that multiplication by hand. 2.7 times 3.01, but that's going to give me 8.127 times 10, 6 plus 6, 12th power. So I can multiply those two millions of numbers, and I don't have to track all those zeros. But now if I wanted to go back to that, I could always, move it back, if for some reason that was important to me, 1, 2, 3, and then 9 more zeros, 1, 2, 3, 1, 2, 3, 1, 2, 3, boom, 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 boom. So, what is 2.7 million and 3.01 million multiplied together? What's that? Thousands, billion, 8,127,000,000,000. But multiplying it with just this format is a lot easier than trying to track all those zeros if I try to do it the other way. Let me do another multiplication. Let's say we had, I'm just going to go into scientific notation here. Let's say I had 7.4 times 10 to the 24th power. I'm going to multiply that by 3.1 times 10 to the negative 6 power. So here I'm multiplying a very big number times a small number. Same thing as before. You're going to take 7.4 times 3.1 times 10, and then the way you multiply these two is you add those powers. Usually we don't like negative exponents. Scientific notation is one of those places where it's okay to have a negative exponent if you get one. But normally, like with those variable expressions I simplified at the beginning, we would not like to leave those with negative exponents. All right, so let's multiply these. 7.4 times 3.1. That's going to give us 22.94 times 10 to the 24 plus negative 6 is 18. And if you wrote your answer this way, you would be almost correct. The problem here is this is not scientific notation. It is close, but in order to be scientific notation, we can only have one digit. We need a single digit, and here we have 2. So this is not scientific notation. So what we would need to do is rewrite this as 2.294 times 10, so we move the digit one spot to the left. And you can kind of think of like what this is saying is like, you imagine I had all these zeros. I counted over 18 spots, and I got here, and I need to count one more over, so 19th power. And you can also do division with this scientific notation stuff if you wanted to say, let's let's take, oh, I don't know, 6.024 times 10 to the 11th, and we're going to divide that by 3.12 times 10 to the negative 4th. Then what we would do is we would take the number parts in front and divide those. And then our answer would be that whatever that answer is times 10 to the 11 minus your denominator exponent of your power of 10. And we would get, and hopefully this doesn't divide out too nasty, divided by 3.12. It did. Okay. So we'll just round, you know, round it, just because I don't want to redo this problem, but with a nicer number. But let's say 1.93 times 10 to the, and again this is plus, so 15th power. So it's about 1.93 times 10. You know, hopefully the problems you would be doing would actually come out to be a halfway decent number, but I just made these numbers up off the top of my head. But you can kind of see how you can use that scientific notation to work with bigger and smaller numbers. All right, so thanks for your time.